At 6:15 on Friday evening, a support engineer asked an internal AI agent to investigate a backlog of failed refunds. The browser showed a spinner, the engineer closed the tab, and everyone went home. The agent did not. It kept reading tickets, calling the model, retrying tools, and opening new investigations for the results it had just created. By midnight, it had produced hundreds of duplicate tickets, and a bill large enough to make the finance dashboard look personally offended. Nothing had crashed. Every service returned success. The failure was architectural. A long-running business process had been implemented as a request handler with a while loop and a collection of powerful credentials. In this SystemSignal breakdown, we will reconstruct the runaway loop and design a backend that treats an agent run as a durable, observable, and cancelable operation. We will separate the user connection from the run, store decisions as events, route model calls through one gateway, place every tool behind policy, isolate generated code, require approval for risky actions, and enforce hard budgets. The goal is not to make a model perfectly predictable. That would be a short video about wishful thinking. The goal is to build ordinary distributed systems, controls around an unusual decision maker. The fictional run made 47 planning passes, 1,800 tool calls, and 312 duplicate tickets. The visible cloud bill was $1,284, but the more expensive cost was uncertainty. Engineers could not answer which tool call belonged to which decision, whether closing the browser should have canceled the work, or whether restarting the API would repeat completed actions. The logs contained request IDs, but the business operation had no durable run ID. The system could count tokens and HTTP responses. It could not explain the agent's state. An agent that can continue, retry, and act needs the same things as a payment workflow: identity, durable progress, bounded retries, and an audit trail. The unsafe architecture looks reasonable in a demo. The browser calls an API. The API starts a loop in memory. Each pass asks a model what to do next, executes the selected tool, appends the result to context, and repeats until the model says done. But the HTTP connection, the process memory, and the business run now share one lifetime. If the connection disappears, should the work stop or continue? If the process restarts, where does the loop resume? If a tool succeeds and its response is lost, can the activity be retried safely? The design has no durable answer, so every failure becomes a guess made with production credentials. The first correction is conceptual. An HTTP request is a delivery attempt. An agent run is the business operation. The request may start a run, query it, stream its events, or ask to cancel it, but it must not own the run's state. This is the same distinction we use for video rendering, order fulfillment, and money movement. The API should return a stable run ID quickly. A separate orchestrator advances that run through explicit states. Closing the tab only closes the observer, unless the user sends a real cancellation command. This separation also makes mobile reconnects and server restarts boring, which is exactly what we want from production infrastructure. Current OWASP agent guidance focuses on excessive functionality, excessive permissions, and excessive autonomy. MCP guidance similarly keeps security decisions in the host and forbids casually passing credentials through trust boundaries. The architectural lesson is simple. Prompts are not authorization policies. A model may propose a tool call, but a deterministic broker must decide whether that run, user, and current state are allowed to perform it. Read tools and write tools should be separate. Credentials should be scoped and short-lived. High-impact actions need independent approval. Generated code should see neither raw tokens nor unrestricted network access. The model can suggest. The backend remains responsible for consequences. The real incident was a feedback loop. The planner opened a ticket for every refund that looked suspicious. Creating a ticket omitted an event. The agent subscribed to those events as new evidence, so it investigated the ticket it had just created and opened another ticket. Slow responses triggered retries, adding a second path through the loop. There was no maximum step count, no duplicate action key, and no rule preventing the run from consuming its own output. The model did not invent an exotic exploit. It followed available signals in a system that had forgotten to distinguish cause from consequence. A small loop became an overnight incident because nothing in the backend could say enough. A governable run needs 4 controls. First, stable identity. Every run and external action receives an idempotency key. Second, an event journal. Decisions, tool requests, approvals, and outcomes are recorded durably so recovery can rebuild state without repeating completed effects. Third, policy enforcement. The tool broker checks the user, run, tool, arguments, and risk class before execution. Fourth, hard budgets. Maximum steps, tokens, wall clock time, concurrent calls, and write operations. These limits are enforced outside the model. Asking the model to remember its budget is like asking a toddler to manage the cookie inventory. Optimism is admirable. An independent counter is better. Here is the production architecture. Clients use the Agent API to start, observe, and cancel runs. The API creates a durable run record and returns immediately. A workflow orchestrator advances explicit state and can recover from its event history after a worker failure. Model calls go through one gateway for routing, rate limits, caching, redaction, and usage accounting. Proposed actions go to a policy and tool broker, never directly to production systems. The broker evaluates authorization, risk, approval, and idempotency. Isolated workers receive narrow capabilities rather than reusable credentials. Every result becomes an event, and the run store remains the source of truth. MCP servers can sit behind the broker as standardized tool adapters, but the host still owns policy and consent. Budgets make the system predictable. A run might allow 24 planning steps, 12 tool calls, 3 write actions, and 2 approval gates. Those example values depend on the product, but the enforcement pattern does not. Reserve budget atomically before dispatching work, so concurrent workers cannot all spend the final unit. Track model tokens, tool latency, retries, and wall clock times separately. When a limit is reached, transition the run to a clear state such as awaiting approval, budget exhausted, or failed safely. Do not silently truncate the agent's history and hope it becomes economical. A bounded failure is diagnosable. An unbounded success response can be surprisingly expensive. The production design adds machinery, so it should earn its place. A simple read-only assistant may not need a workflow engine or isolated workers. But once an agent performs long-running, expensive, or irreversible actions, these controls become cheaper than incident response. The model proposes the next step. The orchestrator decides when the run advances. The broker decides whether the action is allowed. The worker executes one bounded capability. The journal records what happened. Open telemetry style spans connect the run, model operation, and tool call without automatically storing sensitive prompt content. This division gives teams something prompts cannot provide: independent enforcement and an explainable history. The runaway agent was not fixed by a better sentence in the system prompt. It was fixed by giving the agent a real backend. Separate the request from the run. Give every run durable identity and an event history. Use replay to recover decisions, not to repeat external effects. Root model calls through a gateway. Put tools behind deterministic policy and least privilege credentials. Isolate generated code. Require approval for high-impact actions. Reserve budgets atomically and make cancellation an explicit state transition. Protect every write with idempotency. Finally, connect model calls, tool calls, and workflow events in one trace so operators can answer what happened and why. In an interview, the key sentence is this: an LLM is a planner inside the system, not the system's control plane. If you enjoy clear explanations of complex engineering problems and important developments in technology, subscribe to SystemSignal. We publish a new visual breakdown every week.